Welcome to lesson DN1, Free Body Diagrams. Before we begin, we have to talk about newtons. The unit used to express force is a newton, symbolized by a capital N. It is defined as the amount of force required to accelerate 1 kilogram of mass 1 meter per second squared. Instead of writing, when we're looking for force, the unit kilogram meters per second squared, we just write a capital N. Dynamics. We have already looked at kinematics, the study of how objects move. Now we are looking at dynamics. It's the study of why objects move. Newton is credited with bringing about the first laws of dynamics. He recognized, as all people did, that objects move. But unlike his predecessors, Newton was the first to make laws that explain why objects move. The terms associated with why objects move are mass, force, momentum, and kinetic energy. Newton's first law of motion: a body at rest stays at rest, and a body in motion stays in motion unless some external force is applied to it. A force is a push or a pull exerted on an object. This car has 4 forces acting on it at this moment. The force of gravity is pushing down on the car, and in an equal and opposite direction, the earth is pushing back up on the car. There's also a force pulling on the front of the car and a force pushing on the back end of the car. There is no net force if the forces acting on the object completely cancel each other out. The object will behave as if no force is acting on it, and its velocity and direction will not change. Here's Walter sitting in his car. Force of gravity is pushing down. The normal force, the force of the earth, is pushing back up. They are equal and opposite, so they cancel each other out. So as he sits in that car, he does not move. He was not moving. These forces are acting on his car. He remains not moving because they cancel each other out. A force can cause an object to change shape, speed up or slow down, stop, start, or change direction. This may also occur if the forces acting on the object are not equal and opposite. Here's Walter sitting in his car. He is not moving. But then this guy starts pulling. This guy starts pushing. All of a sudden, Walter is starting to accelerate to the left. Since the forces are applied in a specific direction, they are vector quantities, and when multiple forces are added to an object, the net vector can be calculated. Again, here's Walter in his car, force of gravity pushing down, normal force pushing up, this guy's pulling left, that guy's pushing left. Let's say the force of gravity is 28,000 newtons down, the normal force is 28,000 newtons up, the guy pulling is pulling with a force of 210 newtons to the left, and the guy pushing is pushing with a force of 270 newtons to the left. Since the force of gravity is pushing down and the normal force is pushing up, and they are equal to one another, they will cancel out. That means the net force acting on Walter as he's sitting in this car is 480 newtons to the left. Since forces may be applied from all directions, it is often hard to distinguish the net result. Physicists often draw free body diagrams to help determine the net force acting on the object. Although this is an option for physicists, it is not for high school students. You must always draw free body diagrams to accompany your problems. And since we are often referencing directions, our diagrams should also include a coordinate cross. Example 1. 2 dogs pull on a chew toy in opposite directions. The pug pulls with a force of 27 newtons west, and the poodle pulls with a force of 13 newtons east. That's right. It is pug versus poodle. What is the net force acting on the chew toy? We're going to start by making a force diagram sketch. These are mandatory in post-secondary courses. A lot of people waste a lot of time drawing their diagrams. This is what a chew toy looks like. Boop, it's a box, and then I just draw the 2 forces acting on it. 27 newtons pulling west, 13 newtons pulling east. So my net force equals the force applied by the pug plus the force applied by the poodle. Force applied by the pug is 27 newtons west. Force applied by the poodle is 13 newtons east. West is winning, so I switch them both to west. So 13 newtons east becomes negative 13 newtons west. I then take 27, I subtract 13 from it. The overall force is 14 newtons west. Example 2. 4 forces are acting on an object simultaneously. Determine the net force acting on the object. I have a 13 Newton force pulling north. I have an 11 Newton force pushing north. I have a 14 Newton force pulling west, and I have a 19 Newton force pulling east. The 13 Newtons and 11 Newtons are both north, so north is going to win. The 14 Newton force and the 19 Newton force are pulling in opposite directions. So I will have to switch them both to east because east is going to win. So 14 newtons west becomes negative 14 newtons east. So 13 newtons and 11 newtons north added together gives us 24 newtons north, and negative 14 newtons east plus 19 newtons east gives us 5 newtons east. Now I will draw that final vector. I will start by going 24 newtons north, and then 5 newtons east. I will draw my resultant vector. Now I want to find the length of that resultant vector, so I'm going to solve using Pythagorean's theorem, a squared plus b squared equals c squared. So 24 squared plus 5 squared equals, and then I square root that answer, and the length of the hypotenuse is 24.5 newtons. Now I want to find a direction. I always find the direction from where I started. So I'm looking for this angle. I'm going to be using tangent because I know the opposite and adjacent side. So I'm going to be using inverse tan of opposite over adjacent. So I'll take the inverse tan of 5 over 24, and that gives me 11.8 degrees. I'll write north first because I went north, and then I went east. I always write the direction that I went first, then I write the angle, then I write the direction I went second. So north, 11.8 degrees east, and that is my final answer. Example 3, determine the net force. I'm going to draw out all 3 vectors. I've got a 30 Newton force pushing west. I've got a 30 Newton force that is directed east 35 degrees towards the north, and a 40 Newton force directed east 35 degrees towards the south. The first thing I'm going to want to do is break up the 2 vectors that are going on an angle into their north-south, east-west components. So I'll start with 30 newtons east, 35 degrees north. So I go east first, and then north. The angle is going to be 35 degrees, and the overall force is 30 newtons. So I'm going to use sine to find the opposite side, and then I'll use cosine to find the adjacent side. I'll do the same thing with the 40 Newton vector. I go east first, and then south. I draw the resultant vector, which is 35 degrees south of the eastern direction. I'll use sine to find the opposite side. I'll use cosine to find the adjacent side. Now I see I have a west, east, and east component, so I will write those 3 together. I have a north and a south component, so I'll put those 2 components together. Now, if I look at west, east, and east, I see east is going to win, so I switch all 3 of those vectors to east, so 30 newtons west becomes negative 30 newtons east. And between the north and south, the south is going to win, so I'm going to switch both vectors to south. So 17.207 newtons north becomes negative 17.207 newtons south. Now I'll add the east vectors together, and that gives me 27.341 newtons east, and I add the souths together, so 22.943 subtract 17.207 gives me 5.736 newtons south. Now that I have just two vectors left, I'm going to find out what that resultant vector is by drawing that triangle. So first I'm going to go east, 27.341 newtons, and then I'll go south, 5.736 newtons. I'll draw my resultant vector. To find the value of that side, I will have to use a squared plus b squared equals c squared, and that gives me 27.9 newtons. And to find the angle, so I know the direction this is traveling, I will use tangent. So inverse tan of opposite over adjacent, so inverse tan of 5.736 over 27.341, and that gives me east 11.8 degrees south. East because that's the direction I went first, south because that's the direction I went second, and that is my final answer. That brings us to the end of the lesson. You are good to start the DN1 assignment.